Really a head-scratcher,
Yeah,
wave-particle duality.
it's a good one.
This is this wild idea in physics that the tiniest bits of matter, like electrons, can be both wave and particles.
Right.
It's like saying that a basketball could be bouncing like a ball and also be like a ripple in a pond at the same time.
Yeah.
So you actually requested this deep dive to try and understand wave-particle duality.
Yeah, it's one of those things that just like really challenges how we normally think about the world.
Right.
Like, how can something be two things at once?
Yeah, and to get started, we actually need to rewind the clock way back to the really early days of physics,
Okay.
because this debate about whether light is a wave or a particle has actually been going on for centuries.
Yeah, yeah. For a long time, even Isaac Newton, the guy who,
Oh, wow.
figured out gravity, was already weighing in on this.
So Newton was on the side of particle.
That's right. He thought light was made up of these tiny little particles he called corpuscles.
Corpuscles, okay.
And, for a while, his idea was the one that
Yeah.
most people believed.
But there was another contender, right?
Oh,
In
absolutely.
this, scientific showdown. So
Yeah.
who was that?
Christiaan Huygens,
Okay.
he was team wave all the way.
Okay.
He argued that light behaves like waves. Like how sound waves travel through the air?
So it was really team particle versus team wave.
It was, yeah.
Like that was the scientific community?
It was a big debate.
And it sounds like it was pretty evenly split, too.
For a while, yeah.
Okay.
Until 1801, when Thomas Young did his famous double-slit experiment.
Okay, the double-slit experiment. I think I remember
Yeah.
hearing about that in school, but can you refresh my memory?
Yeah, so essentially what Young did was he shined light through two very tiny slits.
Okay.
And then he looked at the pattern that the light made on a screen behind those slits.
Okay.
And what he saw were these alternating bands of light and dark called interference patterns.
And interference patterns are like
Yeah.
a signature of wave behavior, right?
Exactly. Think about like two sets of ripples in a pond overlapping.
Yeah.
You'll get areas where the waves combine to make bigger peaks, the bright bands, and then areas where they cancel each other out, the dark bands.
Yeah.
So it's a classic wave phenomenon.
So that's it then.
Yeah.
Mystery solved, light is a wave.
Yeah.
End of story.
But the plot thickens.
Oh, no.
We're going to fast forward now to the early 1900s
Okay.
and enter Max Planck,
Okay.
a physicist who was studying black body radiation.
Black body radiation?
Yeah.
That sounds a little intimidating.
It sounds fancy, but it's basically the light that's given off by an object when it's heated,
Okay.
like the glow from a hot stovetop.
Got it.
The problem was that classical physics couldn't explain why this light had the specific colors that it did.
Okay.
The predictions just didn't match what scientists were seeing.
So what did Planck do?
He did something pretty radical. He proposed that energy, at least when it comes to light, isn't this like continuous flowing thing. Instead, it's bundled up in these like discrete packets called quanta.
Oh, interesting.
Yeah, and that's where we get the word quantum from.
Oh.
So instead of a smooth stream of energy,
Yeah.
it's more like tiny little bundles of energy.
It's like saying you can't just pour any amount of water into a glass.
Right.
You have to add it in specific amounts.
Yeah, like fixed amount.
Yeah.
That's a great analogy. So Planck's discovery kind of cracked open the door to this whole quantum world.
Yeah.
But it was really Einstein
Okay.
who blew things wide open.
Of course, Einstein.
Of course, had to be Einstein.
So how did Einstein change things up?
Well, he took Planck's idea of quantized energy
Okay.
and apply it to light itself.
Okay.
So Einstein proposed that light isn't just a wave, but it's often made up of these tiny packets of energy, which we now call photons.
Wait, so you're saying light is both a wave and a particle?
Yep.
That's crazy.
Mm-hmm. It is.
My brain is doing backflips right now trying to understand that.
It's a lot to take in.
Yeah.
But Einstein wasn't just throwing out like crazy ideas.
Right.
He had evidence.
Okay.
He used this photon model to explain something called the photoelectric effect.
Photoelectric effect.
Yeah.
Okay, break it down for me.
Yeah.
What is that and how does it support this idea of photons?
Okay, so it's actually pretty straightforward.
Okay.
When you shine light on a metal,
Uh-huh.
sometimes it can actually knock electrons loose.
Okay.
But the weird thing is, how energetic those electrons are doesn't actually depend on how bright the light is.
Huh.
It depends on the color of the light.
Oh, that is unexpected.
It is.
You would think brighter light would mean more energetic electrons.
Right, you'd think like the brighter the light, the harder it knocks those electrons loose.
Yeah.
But that's not what happens.
Okay.
Einstein explained this by saying each photon, each little packet of light, carries a specific amount of energy.
Okay.
If that energy is high enough,
Yeah.
which means the light's frequency is high enough,
Yeah.
it can knock an electron loose regardless of how many other photons are hitting the metal at the same time.
So it's like each photon is like a tiny bullet of light,
Yeah.
and if it hits an electron, With enough force, the electron gets ejected.
Yep.
But the brightness just means more bullets, not stronger bullets.
Exactly.
Yeah.
So this is where things start to get really, really mind-bending.
Yeah.
Because now we have light acting like both a wave and a particle.
It's incredible.
It is. It's really crazy.
So then what happens next in this quantum saga?
Well, if light can be both a wave and a particle,
Yeah.
a young physicist named Louis de Broglie started to wonder, what if matter could do that too?
Hold on. You're saying things like electrons and atoms and even like my coffee mug over here could act like waves?
That's exactly what he proposed. This was like 1924.
That's wild.
It is.
We experience matter as solid, tangible stuff.
Right.
How could it possibly be a wave?
It seems counterintuitive, I know.
Yeah.
So what de Broglie suggested was that a particle's wavelength depends on its momentum.
Okay.
So the faster a particle is moving, the shorter its wavelength is.
So even my coffee mug has a wavelength.
It does.
But it's just incredibly tiny.
Incredibly tiny.
Because it's not moving at the speed of light.
Yeah, exactly. So this was a really revolutionary idea.
Yeah.
De Broglie's theory meant that wave-particle duality wasn't just a quirk of light. It was a fundamental property of everything in the universe.
Wow.
That's huge.
Yeah.
But of course, every great theory
Right.
needs some solid experimental proof.
You need more than just a great idea. You need evidence to back it up.
Exactly. And that's where our story continues.
Okay.
With a groundbreaking experiment that really put this theory to the test.
All right, let's hear about it. So before the break, we were talking about how de Broglie had this theory that all matter could act like waves.
Yeah.
But you said we needed some proof.
Right.
What evidence do we have that this wild idea is actually true?
Well, that's where the Davison-Germer experiment comes in.
Okay.
In 1927, Clinton Davison and Leston Germer were studying how electrons bounced off a nickel crystal.
Okay.
And they were expecting to see, you know, like a pretty predictable scattering pattern like you'd get if you were just shooting tiny marbles at a wall.
Okay, makes sense. So what happened?
Well, not exactly. What Davison and Germer saw were these interference patterns.
Wait a minute, you're saying electrons, which we think of as these tiny particles, were creating the same kind of pattern as waves?
That's exactly what they saw.
That's wild.
Yeah, it was the first experimental confirmation of de Broglie's theory that matter can actually behave like waves.
Wow.
And this wasn't just like a fluke or anything.
Right.
Later experiments showed the same thing happening with atoms and even molecules.
So it's not just light, it's everything. It's a fundamental feature of all matter.
Feature of reality, yeah.
So we have proof that matter can act like waves.
Yeah.
But how does that work? Like, what does it even mean for an electron to be a wave?
Right. So to understand this, we have to talk about the wave function.
Okay, the wave function, I gotta be honest, that sounds a little intimidating.
I know, it's it.
Could you break it down for me?
Yeah.
In a way that maybe even I can understand.
Yeah, so think of the wave function as like a mathematical description of a particle's wave-like behavior.
Okay.
So it doesn't tell you exactly the particle is, but it gives you the probability of finding it in a certain spot.
So it's not like we know exactly where the particle is.
No, it's more like a map of possibilities.
It's like a map of possibilities.
Yeah,
okay.
It's like a blurry cloud that represents all the different places that the electron could be.
Right.
And the wave function tells you where the cloud is densest, which is where the electron is most likely to be found.
Okay, I think I'm starting to get it, but doesn't this mean that, like, the universe is really uncertain?
Yeah.
Like, if we can't know for sure where an electron is, how can we predict anything?
Well, it's true that the quantum world is inherently probabilistic.
Okay.
But that doesn't mean we can't make predictions. In fact, the wave function actually evolves over time.
Okay.
According to a mathematical equation that's called the Schrödinger equation.
The Schrödinger equation. Okay.
Yeah, and this equation allows us to calculate how the probabilities change over time.
Okay.
So we can predict how the electron's wave will, like, spread out or interact with other particles.
So we can't know everything with absolute certainty?
Right.
But we can still use the math to make pretty accurate predictions.
Yeah.
Okay.
And this wave-like nature of particles isn't just some theoretical curiosity.
Yeah.
It actually has real-world consequences.
Okay.
One of the best examples of this is the double-slit experiment.
Wait, back to the double-slit experiment?
Yeah.
I thought we already settled that light is a wave.
We did, but remember, we're talking about wave-particle duality for all matter.
Right, of course, not just light.
So what happens when we fire electrons one at a time through those two tiny slits? If they were really just particles, we'd expect to see two distinct bands on the detector screen.
Like two lines of dots, one for each slit.
Right. Yeah, that's not what we see.
What do we see?
We see an interference pattern.
You're kidding.
Nope.
The electrons, even though we're shooting them one at a time,
Yeah.
are creating those same wavy bands.
Exactly.
Like they're interfering with each other.
It's as if each electron is going through both slits at the same time
What?
and interfering with itself.
Wow.
It's one of the most fundamental and mysterious aspects of quantum mechanics.
Okay, so does the electron split in half, go through both slits, and then merge back together?
Well, it's natural to think of it that way.
Yeah.
But it's not quite accurate.
Okay.
In quantum mechanics, we have to be really careful about how we visualize things.
Yeah.
The electron doesn't literally split in half.
Okay.
What happens is its wave function,
Uh-huh.
that blurry cloud of possibilities, spreads out
Yeah.
and goes through both slits.
So it's like the electron's wave function is going on this little adventure
Yeah.
through both slits, and then when it hits the detector screen, it's like, okay, I'm going to become a particle now and pick a spot to land.
Yeah, you got it.
And even though each individual electron is unpredictable,
Yeah.
the overall pattern that we see is completely predictable.
Exactly. That's the beauty of quantum mechanics.
Wow.
It's probabilistic on the individual level, but deterministic on the statistical level.
So this is all incredible,
Yeah,
but it's making my head spin a little bit, to be honest.
I understand.
What are the implications of all of this? Does this mean that we can never really know for sure what's going on?
That's a great question, and the answer is kind of yes.
Really?
The act of observing a quantum system, like an electron, actually influences its behavior.
What, you're telling me just by looking at something,
Yeah,
we change how it acts?
that's right. It's one of the key principles of quantum mechanics.
That's even weirder than the electron going through two slits at once.
I know, but to understand this, we need to talk about another kind of mind-blowing concept, the uncertainty principle.
Okay, the uncertainty principle. So in the last part, we were talking about how the act of just observing a quantum system can actually influence its behavior.
Right. It's one of the weirdest things about quantum mechanics.
It really is. I mean, it's almost like we are part of the experiment ourselves just by watching.
In a way, we are.
And you mentioned something called the uncertainty principle.
Yeah.
Does that have something to do with how our observations can affect the outcome?
Absolutely. So the uncertainty principle was formulated by Werner Heisenberg.
Heisenberg, okay.
And it basically says that we can't know both the position and the momentum of a particle with perfect accuracy at the same time. The more precisely we know one of those things, the less we can know about the other.
It's almost like if you're trying to measure a piece of Jell-O.
Right.
Like the more you try and pin down its position, the more it kind of squeezes it somewhere else.
Exactly. That's a great analogy.
So it's like we're always going to be missing some information.
Yeah, it's not even that our instruments aren't good enough.
Okay.
It's like a built-in feature of the universe itself.
So even with like the most crazy advanced technology, we'll never be able to get a perfect picture of both at the same time.
Exactly. It's not a limitation of our technology. It's a fundamental principle of nature.
So it's not that we're just not smart enough. It's that we can't.
We literally can't know.
Wow. And this uncertainty isn't just some abstract idea.
Right.
It has real consequences.
Absolutely. It's actually the reason why electrons don't spiral into the nucleus of an atom.
Wait, really?
Yeah.
I remember learning in school that electrons orbit the nucleus like planet around the sun.
That's the classical picture.
Yeah.
But it's not entirely accurate.
Okay.
Because if electrons were just these tiny particles orbiting the nucleus, they would constantly be radiating energy, and they would eventually just spiral inward.
And then the atom would collapse?
Yeah. Base doesn't sound good.
No, it would mean that matter as we know it wouldn't be stable.
Right.
But thankfully, the uncertainty principle comes to the rescue.
Okay.
Because we can't know both the position and the momentum of an electron with perfect accuracy. The electron can't be confined to a single point in space.
Okay.
It actually exists as kind of like a blurry cloud of possibilities.
Yeah.
A wave function that spreads out around the nucleus.
So instead of a tiny planet orbiting the sun, it's more like this fuzzy cloud.
Yeah, like a fuzzy cloud enveloping the nucleus.
Yeah, okay.
That's a much better way to picture it.
So it's this constant movement and change, right?
That actually keeps atoms from falling apart.
Yeah, exactly.
Wow. So wave-particle duality, this seemingly bizarre concept, actually explains why atoms don't just collapse.
It does.
It's amazing how these quantum principles underpin, like, literally the structure of our universe.
It really is.
It's a lot to take in.
I know, but it's amazing, right?
It is. We've gone from this simple question about whether light is a wave or a particle to this incredible journey through quantum mechanics.
It's a wild ride.
Where we've seen how matter can act like waves, how observers can influence experiments, and how uncertainty is actually a fundamental principle of the universe.
Yeah.
What does it all mean? Where do we go from here?
Well, that's the beauty of science. Every answer just leads to more questions.
That's true.
Wave-particle duality has completely changed our understanding of physics.
Yeah.
And it's opened up these whole new areas of study like quantum computing, quantum cryptography.
Yeah.
It's also challenged us to rethink our most basic assumptions about the nature of reality.
It really has. I mean, it's almost like we have to relearn everything we thought we knew.
In a way, yeah.
But it's exciting.
It is.
It really is.
Yeah.
It makes you realize that we are just starting to understand the universe.
I agree.
And there's so much more out there to discover.
Absolutely. The mysteries of quantum mechanics are far from solved, and there's so much we don't understand. But one thing's for sure, the more we learn, the weirder and more wonderful the universe becomes.
That's a great way to put it. So, to our amazing listeners out there, we hope you've enjoyed this deep dive into wave-particle duality.
It's been fun.
It has, and we encourage you to keep exploring, keep asking questions, and never lose that sense of wonder about the universe we live in.
Yeah, stay curious.
The journey of discovery never ends, and there are countless more mysteries waiting to be unraveled.
Definitely.
Until next time, stay curious.